Let's learn about the dot product and what it means. The dot product really is an operation that pertains to vectors. You probably haven't seen the dot product before unless you've dealt with vectors, because the dot product doesn't really mean anything in a scalar system where there are no directions. It's very similar to multiplication, but it's not exactly the same thing. In fact, there's really two operations with two vectors that are similar to multiplication. There's the dot product and the cross product, but we're going to focus on the dot product today. So what will we be able to do with the dot product? Well, when you're done, you should be able to determine the angle between two vectors, and you should be able to calculate the projection of a vector along a specific line, which would essentially be another vector, another direction. Of course, we're not in class, so we can't check homework. We'll not cover the reading quiz either, and I would recommend that you go back after this and look at the reading quiz and see if you can solve it. But we'll talk about what the dot product is used for and applications in the real world and how it's relevant. Then we'll show the definition. We'll talk about how to determine angles and then determine projections. Then we'll have a concept quiz. I'll challenge you to go through the group problem solving quiz, and then we'll go through the attendance quiz. So this is the reading quiz that I would challenge you to go through after you've seen the lecture. So here's an application. If you know physically the measurements of the points on the locations of these four ends of cable, could you calculate the angle between them rather than trying to measure it? It turns out actually you could. Here's another application. If you're applying a force at an angle to a bar, could you calculate how much of that force lies along the length of the bar and how much is at a right angle to the direction of the bar? That's another thing that the dot product is useful for. And basically by calculating the parallel component, we're able to deduce the perpendicular component. So now let's explore the definition of the dot product. So we've got vector A and B, and they are at some angle theta with respect to one another. We don't really care about the coordinate system per se, that doesn't matter. It's just that there's some angle, and of course vectors A and B being straight lines would form a plane. So we're just interested in the angle within that plane. So how do we define it? Well, the way we write it is as vector A dot vector B, and it turns out that it is equal to the magnitude of vector A times the magnitude of vector B multiplied by the cosine of the angle between them. Now the angle theta is the smallest angle between the two vectors, as I said, because it lies in a plane defined by A and B, and it will always be in a range of 0 to 180 degrees. So if A turns around opposite of B and then continues turning, then theta's definition would change so that it's the smaller definition. It wouldn't go above 180 degrees. What do you get out of a dot product? Well, the result of the dot product is always a scalar. So you put two vectors in and you get a scalar out. The units of the dot product will be the multiplication of the units from the two vectors. So if you have, say, pounds and feet as the two vectors, then the resulting units will be pounds times feet. Now, it's important to realize that we always write vectors with regard to a coordinate system. So we've always got unit vectors to deal with. So when you calculate the dot product of the two vectors, what you actually do is take each of the components that point in the same direction and multiply them by each other. So for example, we've got vector A, vector B. We would take AX times I times BX times I. So AX times BX, that's no big deal. Those are scalars. You know how to deal with that. It's just buttons on your calculator you have to press if AX and BX, of course, are represented by numbers. But what about I times I? What is that? Well, really, the dot product is a projection of one vector on the other. And since I times I, or I dot I, is the same thing, right? I mean, I is I, it's going to have 100% of its length on the other vector. And so the dot product of I with I is 1. The dot product of K with K is 1. The product of J with J is 1. But any vectors that are at right angles to each other have no projection on the other. They're basically a point on the other line. And so I dot J, for example, is 0. So you can think of the dot product as a projection. And so all you really do to take the dot product of two vectors is just take the components that are in the same direction, like ax and bx, multiply them together, and then you add to that the product of all the other components in the other direction. So plus ay by plus az bz. So how do we use the dot product to determine the angle between two vectors? Well, it's pretty straightforward. First of all, take the two vectors, calculate the dot product, calculate then the magnitudes of vectors a and b, and then all you really need to do is divide the dot product of the vectors by their magnitudes, because that will normalize the vector or make it between 0 and 1, and then take the inverse cosine. So it's actually very simple to calculate the angle between two vectors once you've taken the dot product of those two vectors. Now, if what we're interested in is just the projection of a vector on another line, that's pretty straightforward. You can think of projections as the sun shining down perpendicular to line AA, and we're just looking at the shadow of vector A on line AA. That's what the projection is. It's a pretty simple thing. And the way you calculate it is with the dot product. So the first thing to do is to find the unit vector that points along the direction where you want the projection, so along AA. After you've got that unit vector, then all you have to do is take the dot product between the vector A and the direction u sub A. Unfortunately, they called it AA. I wish they'd called it XX or something like that, something different, because it's a little confusing between the capital A and the lowercase a. There's no real relationship except that we're trying to find the projection of vector A onto line AA. Maybe they could have called it, I don't know, QQ or something, you know. So one important point, though, is that the vector has to pass through one point on the line in our work. Okay, so to find the scalar projection, in other words, the length of the shadow of A on AA, we take the dot product between vector A and unit vector u sub A. Now all that gives us is a length, because remember that the dot product just gives us a scalar. It doesn't really give us a direction. So if we want that as a vector along AA, so the component of the vector A that is parallel to the line or that lies on the line, then what we need to do is multiply that magnitude we just found by the unit vector u sub A, and that would be the projection of vector A onto line AA as a vector. Now, to calculate the perpendicular component, we can just realize that what we're doing is taking vector A and breaking it down into a triangle, a horizontal and vertical component, a right triangle. So to calculate the magnitude of the perpendicular component, all we have to do is take the length of the vector, which would be the hypotenuse, a squared, subtract off what we've just found, which is the parallel piece along line AA, take that squared, subtract it off, take the square root, and we will have rearranged Pythagorean's theorem and found basically the vertical component of A off of line AA, and that would be perpendicular to line AA. And then if we want to get the perpendicular component as a vector, all we simply do is take vector A and subtract off the vector that lies along line AA. And of course, all we're doing is rearranging the fact that vector A can be made up of the perpendicular plus parallel components. As our first example, we'll consider a force applied to a hook and a coordinate system offset as shown in the figure. Now, it's important to understand what's going on here. It looks like we're interested in the vector from A to O. That'll be our position vector. And that vector, the way we get from A to O is we have to move down along the z-axis, we have to move back along the x-axis, negative x direction, and forward along the y-axis. So we're asked to find the angle between the force vector and that line AO, and also the magnitude of the projection of that force. In other words, how much of force F could be represented as line along line AO, or in other words, what's the shadow of vector F on line AO? So the first thing to do, the way we're going to solve this, is to find the position vector from A to O. Then we're going to calculate the angle between the force and that position vector. And you can see the equation we'll use there. Of course, we'll use the dot product along the way in order to calculate the dot product of the force vector with the position vector, and then normalize it by dividing by the magnitude of those two, then take the inverse cosine. Then what we'll do is find the projection FAO, which is the projection of F onto line AO, by taking the dot product between vector F and the unit vector along line AO. Or we could simply use the magnitude of vector F times the cosine of the angle between them, which we found in step 2. First things first, vector AO, we have to write it down. So if you notice, what we're doing is we're moving -1 meter in the x direction. So follow me, we're at point A, we move back 1 meter along the x direction. So now we're in the XY plane. We move up in the y direction by 2 meters. Now, usually the y direction points up, but in this case it's pointing off to the right. So we have to move 2 meters along y in the positive y direction. And then after that, we have to move down 2 meters in the z direction, down vertically. So that's how we calculate or write down, really, the vector, the position vector, RAO. And then we can calculate its magnitude by simply squaring all the terms and adding them together, then taking the square root. So this position vector is a 3 meter long magnitude. And of course, the force F was given directly, but we need its magnitude, so we do that next. Now, to take the dot product between those two, what we have to do is take each of the components of RAO and F and multiply them between each other and then add, or multiply them by each other and add. So -1 times -6 plus 2 times 9 plus -2 times 3. And you see the result of that is 18. And of course, since the units of the force are kilonewtons and the units of R are meters, then kilonewton meters are the resulting units of this dot product. So then to find the angle between the two vectors, don't forget, you can't just take the dot product. You got to take the dot product divided by the magnitude of both vectors so that you're taking out the units, you're normalizing the vector and producing a vector that's between 0 and 1, and then take the inverse cosine. So we know that 18 kilonewton meters is the length, it's the scalar length of F dot RAO, and then we have to divide by the magnitude of the force, which is 11.22 kilonewtons, and divide by 3 meters. So you see that's what's done there. Then take the inverse cosine. We find that the angle between those two is 57.67 degrees. Okay, so then what? Well, don't forget that we also want the projection of F onto RAO. So let's do that next. We need the unit vector along RAO. So all we do is take the vector RAO and divide it by its magnitude. Remember, its magnitude was 3 meters. So each term in the vector gets divided by the magnitude. So we have -1/3 I plus 2/3 j plus a -2/3 k, or in other words, -2/3 k. Then, if we want to calculate the projection of the force onto line AO, what we will do is take the dot product between the force and the unit vector, UAO. And so you see that's what's done here. Remember that force F has components -6I, that gets multiplied by the -1/3 in the I direction for the position vector, then plus 9 kilonewtons in the j direction times 2/3 of a meter. Well, it's not meters anymore, right? We've normalized it, so actually by 2/3 non-dimensional. And then plus 3 in the k direction times -2/3 from the unit vector UAO. And so we end up with the same units, kilonewtons. I almost made the mistake of thinking that we were still dealing with a position vector dotted with a force vector. But it's not. It's a force vector dotted with a unitless unit vector. And so that's kilonewtons as our result. If you do the math, you come out to 6 kilonewtons. Now, try it yourself, but if you take the magnitude of force F and multiply it by the cosine of the angle that we found before, theta, 57.67 degrees, you get the same answer of 6 kilonewtons. So we've done everything that was asked of us. We found the angle between the force and the position vector, and we have calculated how much of force F lies along line RAO. Now, if we wanted to in that problem, we could actually continue and calculate the vector, the rest of the force that is perpendicular to that line, but we didn't do that. Here's example 2. It's a similar problem. We've got a force acting at the end of a pole at point A, and we're supposed to find the components that are acting parallel and perpendicular. So this is very similar to the last example, except we're going to go farther. And of course, we're in English units this time instead of metric units, but the same principles apply. Now, it's really important to kind of wrap your head around what's going on here. This is a 3-dimensional picture and rendered on a 2-dimensional surface. So if you look at AO, you notice that we've got coordinates x, y, and z. So O to A has a component in the negative x direction. Let's see, positive y and positive z. Whereas the force F, you notice the plane beneath F that contains the 30-degree angle, that plane is actually parallel to the xy plane. So the 60-degree angle you see is an angle that would, if we had F in the xy plane, we kept rotating it past 60 degrees. If we rotated it 30 more degrees, then F would be parallel to the z-axis. But that plane that contains F and contains that 60-degree angle is at an angle going, it's in a plane going through z, but at an angle to the y-axis. In fact, that angle is 30 degrees. So we're supposed to find the force acting on the pole, we're given that. We're supposed to find the components of the force that are parallel and perpendicular to the axis of the pole. So the first thing we'll do is find force F, determine the position vectors and the unit vectors. Then what we'll do is determine the parallel component using the dot product, and then the perpendicular component by subtraction. All right, so first things first, write ROA. So let's see, -4 in the I direction, that's the negative x direction, +4 in the j, yes, that makes sense, moving forward along the y-axis, and then up 2 feet in the k direction. And I just noticed that we've got meters here. We should actually have feet, not meters, so that's a mistake in the slides. Numerically, it should be okay, though, because I know those numbers are right. Then we just find the magnitude, 4 squared plus 4 squared plus 2 squared square root, should be 6 meters, 6 feet. And then the unit vector we can find by simply normalizing the position vector, ROA, by dividing each of the terms by the magnitude. So -4/6 is the same thing as -2/3 in the I direction. Same thing for j, except of course it's positive. 4/6 is 2/3. And then for the last term, 2/6 is 1/3. So now we found the unit vector along the pole. Now you need to pause and look at this to make sure you understand it, but to calculate or to determine the components of the force F, what's being done here is the 600-pound force is first of all being projected onto a plane that is perpendicular to the xy axis. That's that plane I mentioned before that contains the 30-degree angle. So you see the angle that says 60 degrees. Well, that's what we're doing here. We're basically taking the projection of F onto that line that goes down to 60 degrees, and then that line continues over 30 degrees until it's parallel to the y-axis. Okay, so to calculate the projection of that force, that 600-pound force, onto that elevated plane that's elevated by 2 feet, fortunately they used pounds here, so they did that right, but 600 times cosine of 60, because notice the 60-degree angle is touching the line along which we want that component of the force. And then after that, in order to calculate the component of that's along the x-axis, they took the sine of 30 degrees, and of course you attach a negative sign because it's a component pointing in the negative x direction. A similar story for the y component, because you got to first take that 600-pound vector, put it down into the plane. That's what 600 cosine 60 does. And then cosine of 30 calculates the component in the y direction that is touching the 30-degree angle. And then finally, the vertical component of the 600-pound force is pretty straightforward. It's just 600 sine of 60 degrees. It's the other component instead of the cosine component. If you do the math, plug it into your calculator, you find the magnitude shown there for the I, j, and k directions. Okay, so then to calculate the parallel component of F along the pole, flagpole, whatever this thing is, we need to take the dot product of the force with the unit vector along that direction, that line where we want it. So we just basically multiply the magnitude of each of the components, like the I components, -150 times -2/3, and then 259.8 times 2/3, and so on, add them together to find the magnitude of the scalar size, the length of, not the length, but the magnitude of vector F that lies along line OA. And you see that's 446 pounds. So that's the component of the force F projected onto line OA. So now we've got the magnitude of the force. We've got the magnitude of the force that's parallel to the pole. If we want to get the magnitude of the force that is perpendicular to this pole, then we'll just treat it as a triangle, take the square root of the sum of the squares, and rearrange it, of course. So the magnitude of the force, square of the magnitude of the force minus the magnitude of the force that is parallel to the line, quantity to the half power, and that's 401 pounds. Now let's go through the concept quiz. If a dot product of two non-zero vectors is 0, let's see, Dot product of two non-zero. So they both have length. We're taking the dot product. What the dot product does is it tells us how much one vector projects onto the other, essentially. Okay, so dot product, if it's 0, what does that mean? Well, that means that there's basically just a point from one vector on the line of the other, right? It's 0 projection. How could you get a 0 length shadow? Well, it's easy. Just have the sun directly overhead, right? If you have a pole sticking up, how do you get a 0 length shadow? Well, sun directly overhead will do that, right? And so what that means then is that the pole is perpendicular to the ground. So if we're talking about vectors then, if we get a dot product of 0, then they must be perpendicular to one another. So that's answer C. If a dot product of two non-zero vectors is equal to -1, then the vectors must be what to each other? Well, let's see. Dot product is -1. That's 100%. That means that they're at least collinear. But if it's negative, then what that means is one vector points one way and the other vector points in the opposite direction. So collinear but pointing in the opposite direction would be the answer I would choose. Notice parallel pointing in the opposite direction doesn't work because for a vector to have a dot product that's non-zero, they have to touch at one point at least. Okay. Now here's a group problem solving problem. I would suggest that you pause the video and try to read this and find the result that's requested and see what you can do. And if you've got some friends or fellow companions in the class that you're watching this video at the same time, maybe you could work with them. So finally we come to the attention quiz. Let's see what the questions are. Question 1, the dot product can be used to find all of the following except. Well, let's see, sum of two vectors. Not sure. How about B, the angle between two vectors? Yes, definitely. We've done that already. The components of a vector parallel to another line? Absolutely, we did that too. Component of a vector perpendicular to another line? Yes, we did all of those. So A would be the one that doesn't work. To find the sum of two vectors, all you do is just add the components. So summing vectors is like addition, whereas dot products are like multiplication. Okay. Find the dot product of the two vectors P and Q. Okay, so to find the dot product, all we need to do is take each of the components and multiply them by each other and then add. So for example, 5i times -2i, well, I dot I really is just 1. So 5 times -2 then is -10 times 1 then is -10. But then we need to add to that 2 times 5 from the j component or the y component, so they just cancel out. And then lastly, we need 3k times 4k. Well, k dot k is 1, 3 times 4 is 12, 1 times 12 is 12, and the units we would expect would be meters times meters, so meters squared. The only answer that matches that is C, and so our answer is 12 square meters.